When we hear a sound, we witness a brutal, physical action. At the exact fraction a sound is made, an object violently shudders. To understand why that shudder matters, we have to look at the environment of outer space, far above the Earth's atmosphere. If an astronaut working outside a station strikes a metal wrench against a steel beam, the wrench will still physically bend, it will still rapidly shake. Yet, this impact produces an absolute silence. Sound is a systematic production. Without a physical medium surrounding the wrench, like a thick blanket of air or water, the kinetic energy from that strike has nowhere to go. Every sound you have ever heard originates from this exact physical requirement, a rapid, periodic to and fro motion, a vibration, against a surrounding material. Whether it is the fluttering of vocal cords or the bounce of a drum skin, the origin of sound is always a periodic back and forth motion, scientifically defined as an oscillation. The tuning fork provides the purest visual example. It is engineered so its rigid metal prongs snap back and forth at a precise, measurable rate when struck. By placing those vibrating prongs against the surface of a liquid, we can see the invisible kinetic energy being transferred out of the metal, creating visible ripples in the surrounding environment. The source of any sound is this physical shoving of the immediate surroundings. But an object vibrating on a desk is only the beginning. To bridge the gap to our ears, the to and fro motion of the source must cross the room through a medium. In this starting state, the air particles in a room are evenly distributed at a uniform average density. The outward snap of the vibrating object shoves the nearest air particles, packing them into a high-density region called a compression. As the object snaps backward, it leaves a low-density space behind the compression called a rarefaction. Crucially, the air particles don't travel to your ear. They newly collide with neighbors, pass energy forward, and bounce back to their original position. Sound travels as a wave of pure kinetic energy, passing like a chain reaction through the medium. The physical dimensions of the source's movement dictate the specific characteristics of the sound we ultimately hear. We can plot these density variations on a graph. The speed of the vibration determines the frequency. A faster oscillation creates closely packed waves, which our brains perceive as a high-pitched squeal. The physical strength of the swing dictates the amplitude. A harder strike carries more energy, creating larger density changes and a higher intensity sound. Pitch and loudness are the direct mathematical translations of the source object's mechanical speed and physical distance. Pacing slows slightly, more focused. This wave of alternating compressions and rarefactions eventually reaches the end of its journey at the side of a human head. When these pulses enter the ear canal, the alternating air pressure physically pushes and pulls against a thin membrane called the eardrum. This creates a profound mimicry. The eardrum is forced into the exact same to and fro motion that the original object performed across the room. Tiny bones amplify this mechanical vibration, and the cochlea converts the movement into electrical signals for the brain. Sound is an unbroken, invisible bridge of physical movement. When someone speaks to you, they are setting off a kinetic chain reaction that physically manipulates your eardrum. To hear a sound is to be physically touched from across a room.